Hey y'all, welcome to video 19. Today we're diving into multi-threading, making your programs do multiple things at once. Fair warning, this is where programming gets interesting, and by interesting, I mean potentially maddening, but don't worry, we'll work through it together. So far, every program we've written has done one thing at a time, step by step, but modern computers have multiple CPU cores, and your code should take advantage of that. Let's learn how. A thread is like a worker in your program. Up until now, you've had one worker doing everything sequentially. Read this, calculate that, write something. Multithreading means hiring multiple workers to do different tasks at the same time. Your CPU probably has 4, 8, or more cores. Without multithreading, you're using just one while the others sit idle. That's like having a team of workers and only letting one person work while everyone else watches. Here's the thing. Multiple threads can access the same data simultaneously. When two workers try to update the same variable at the exact same moment, chaos. This is what makes multithreading one of the hardest topics in programming. I'm going to show you exactly how things go wrong when threads compete for resources. These bugs are called race conditions, and they're absolutely maddening because they're intermittent and hard to reproduce. We'll cover the basic tools for keeping code threads safe, the lock statement, understanding atomic operations, and knowing when you need to worry. This is foundational stuff everyone needs to know. All right, buckle up. This stuff can be mind-bending at first, but I promise we'll make it click. Even your simple console apps are already using multiple threads behind the scenes. The garbage collector runs on its own thread. Finalizers get their own thread. Timer callbacks? Another thread. Your single-threaded app isn't really single-threaded at all. The runtime is doing a lot of work behind the scenes, and once you understand that, threading makes a lot more sense. Here's how we can see what threads are actually running in our process. Every program starts with one thread, the main thread. This is where your main method runs. It's been doing all your work so far, executing one line at a time. Every thread has a manage thread ID. Thread 1 is typically your main thread. You'll see this ID in debug output and exception messages. It's super helpful for tracking which thread caused a problem. Run this code and you'll probably see 5 to 10 threads, even in a simple app. That's the runtime doing its thing. Garbage collection, JIT compilation, finalizers, all running in the background. Now let me show you the old school way to create your own thread. You probably shouldn't do this in modern code, but you need to understand it first. Warning. This is the primitive approach. Don't do this in production code, but you need to see it to understand what's happening under the hood. You create a thread by giving it a method to execute. That method becomes the thread's job. It'll run this code on a separate thread of execution. The thread doesn't run until you call start. Once you do, the OS schedules it. Might be immediately, might be in a few milliseconds. That's up to the operating system, not you. Watch what happens. Both threads print at the same time. You'll see main and worker messages mixed together in random order. This is true parallel execution happening right in your console. Okay, this works, but it's primitive. Modern C# has tasks which are way better, but first you need to see what goes wrong with threads. Here's a question that keeps developers up at night. What happens when two threads try to update the same variable at the same time? Think about it. Thread 1 reads the value. Thread 2 reads the same value. They both do their calculations. They both write back. What happens to one of those updates? It vanishes. And this happens faster than you can blink. Let me show you exactly how this breaks. Okay, here's where things get dangerous. This is one of those bugs that made me question my career choices early on. That innocent-looking counter plus plus is actually 3 operations. Read the value, add 1, write it back. 3 separate steps where another thread can interfere. Thread 1 reads 100, thread 2 reads 100, both add 1, both write 101. We just lost an increment. This happens thousands of times in our loop. That's why the final count is way off. Run this multiple times. You'll get different results every time. Sometimes 147,000, sometimes 183,000. The exact timing of thread switches determines the final value. This is what makes threading bugs so hard to debug. Let me show you visually exactly how those updates get lost. Here's a step-by-step breakdown of how that increment gets lost. Watch the timing carefully. Counter starts at 100. Both threads want to increment it. Watch what happens when their operations overlap. Both threads read 100 before either writes back. They both calculate 101 and both write 101. We did 2 increments but only got 1. That's the lost update. See the problem? 2 increments should give us 102, but we only got to 101. Multiply this by 100,000 iterations and you see why our final count is way off. This timing problem happens at the CPU instruction level. It's invisible in your code, but devastating in your results. So how do we fix it? The fix is the lock statement. It's kind of like putting a bathroom door lock on your code, only one person at a time. Without the lock, threads step all over each other. You might get 137,000, might get 189,000. Who knows? It's random every time. Locks work, but they're blunt instruments. Let me show you a faster alternative for simple operations. For simple operations like incrementing or adding, there's a faster alternative, the Interlocked class. Check this out. Interlocked uses special CPU instructions that guarantee the entire operation happens atomically. No thread can interfere in the middle. It's way faster than locks for simple operations. Incrementing, decrementing, adding, these are exactly what Interlocked is designed for. Thread-safe counters, statistics, IDs, use interlocked instead of locks. You can't use interlocked for complex logic. It's only for basic numeric operations. For anything more complicated, you need locks or higher level constructs. But when you can use it, it's fast. Interlocked is faster than locks, but more limited. Choose the right tool for the job. Now let me clear up some confusion about what's actually thread safe. This trips people up all the time. Let me give you a quick reference for what operations are naturally safe versus which need protection. Assigning a single value to an int or a reference is atomic. It happens in one CPU instruction. You can't get halfway values. That's the good news. Anything that reads, modifies, and writes back, like counter plus plus or counter plus where it gets 5, these need locks or interlocked. There are multiple operations under the hood. Local variables are on each thread stack. Completely separate memory. Thread 1's local variable can't affect thread 2's. They're inherently thread safe. That's why functional programming patterns work so well in concurrent code. When in doubt, assume it's not thread safe and add synchronization. Better safe than debugging race conditions at 2 a.m. Locks solve race conditions but create a new problem, deadlocks. This is when threads get stuck waiting for each other forever. It's like 2 people at a door, each insisting the other go first. Thread 1 holds lock, wants lock. Thread 2 holds locked, wants lock. Neither can proceed. They're waiting on each other forever. This is a classic deadlock. Deadlocks don't throw exceptions or log errors. Your app just stops responding. Threads are alive but stuck, waiting for locks that'll never be released. This is a nightmare to debug. The fix is simple but requires discipline. Always acquire locks in the same order. If every method locks object, then object deadlocks can't happen. Consistent ordering prevents circular waits. Deadlocks are rare but devastating. Good lock discipline prevents them. Always lock in the same order and lock as briefly as possible. Before we wrap up, let me save you from the mistakes that cause the worst threading bugs. I've made all of these myself. Creating a new thread for each item in a collection? You'll overwhelm the system with hundreds or thousands of threads. Use the thread pool or task parallel library instead. Threads are expensive to create. Thread. Abort kills a thread immediately, possibly mid-operation. It can corrupt data and leave locks held forever. It's so dangerous that .NET Core doesn't even support it. Use cancellation token instead. Locking on this or type of myClass means external code can lock your object. They're public by nature. Create a private object specifically for locking. Always private, never shared. Most .NET classes are not thread safe. List, dictionary, and even string builder, none are safe for concurrent access. Always check documentation before using from multiple threads, and when in doubt, add locks. These mistakes will bite you hard. Learn from others' pain instead of your own. Trust me on this one. Multithreading is one of the hardest topics in all of programming. Race conditions happen randomly and disappear when you add logging. Deadlocks freeze your app with no error message. Bugs show up in production, but never in debugging. Even experts with decades of experience get threading wrong regularly. So if this feels confusing, that's totally normal. It is confusing. Don't feel bad about finding it hard. Everyone does. Good news. .NET provides thread-safe versions of common collections. Next video we'll dive deep into these, but here's a quick preview of what's available. See that concurrent prefix? Those collections are designed from the ground up for multiple threads. No locks needed in your code. They handle all the synchronization internally using clever lock-free algorithms. Blocking collection is special. It's designed for producer-consumer scenarios where one thread adds items and another removes them. It blocks you when empty or full, coordinating the threads automatically. These collections make concurrent programming way easier. We'll explore them in detail next video and see how they work their magic. This is the big one. In ASP.NET Core, every request runs on its own thread. If you have any shared state, static variables, singleton services, you need synchronization. The framework handles request isolation, but shared state is your responsibility. If you're processing data in background threads while the main app continues, and they need to share state, that's when threading bugs appear. Use concurrent collections or message queues to coordinate safely. WPF, Windows Forms, MAUI, they all have a UI thread that must not be blocked. When you fetch data asynchronously, you're using threads. Make sure you marshal back to the UI thread before updating controls. Simple console apps with no explicit threading? You're probably fine. The main thread runs your code sequentially. Unless you're deliberately creating threads or using parallel.4, you don't need locks. Let's recap the threading fundamentals we've covered today. Multiple threads mean multiple pieces of code running simultaneously. This can make programs faster by using multiple CPU cores, but it adds significant complexity. Don't add threads unless you need them. When threads access the same variables without synchronization, you get race conditions. Results become unpredictable and bugs become intermittent nightmares. The fix is simple: synchronize access. The lock statement ensures only one thread accesses critical code at a time. It's simple but effective for basic thread safety. Just remember, locks reduce parallelism. That's the trade-off. Don't create raw threads in modern code. Use tasks, async, and await, or parallel.4. These handle thread pool management and are much easier to use correctly. We'll cover these soon. Next video, we're diving into thread-safe collections. They make concurrent programming much more manageable. Trust me. Here's a challenge to help you understand threading problems firsthand. Sometimes you need to feel the pain to really get it. Build a bank account class with a balance field and deposit and withdraw methods. Start with a balance of $1,000. Keep it simple. Create 10 threads that each perform 1,000 random transactions. Mix of deposits and withdrawals of small amounts, like $1 to $10, let them all run at once. Run it without any synchronization. Print the final balance. It won't be 1,000 anymore. Run it multiple times and watch the balance change randomly. This is the race condition in action. Add proper locking to the deposit and withdraw methods. Run again. The balance should be exactly 1,000 every single time now. Feel the difference locks make. For extra credit, implement it using interlocked add instead of locks. Use stopwatch to measure the performance difference. You might be surprised how much faster lock-free code can be. This exercise really drives home why thread synchronization matters. When you see that corrupted balance, that's when threading clicks. See you in the next video. Thanks for watching.